Welcome folks, I would like to give you a new tutorial on RL step response circuits. Basically we are going to solve example and then we're going to validate the example with PSPICE Orcad simulation. So let's get started. In this example we have the circuit, and the first thing I want you to see when you look at the circuit is that you know that you're going to have some DC voltage sources only. DC voltage sources only, and there is some switching in the circuit. So right away you know that this is going to be a step response because the applied sources to the circuit are DC. They're going to move from one value to a new value to act as a step function because we have switching. Then if you look closely to the circuit, you're going to have only one inductor. There is only one inductor in the circuit, no capacitors, just one inductor, and then bunch of resistors. So by looking into the circuit, if you see DC voltage sources or DC current sources, switching, one inductor, and bunch of resistors, then you know that this circuit, we call it the step response RL circuit. The step response RL circuit. So if you draw the circuit after switching and you apply KVL and KCL, you're gonna have a first order differential equation that look like this. It's gonna be the first derivative of whatever voltage or current you solve in. So we're gonna say that the first derivative of f of t plus, you're gonna have 1 over tau times f of t, 1 over constant. Tau is a constant here. So 1 over a constant times f of t will equal to some constant value k. Now this constant value is basically caused by the DC voltage sources applied to the circuit after switching. That's why we have a constant value. It doesn't matter what circuit technique you're going to have to obtain the differential equation for whatever output you are solving for after switching for t greater than 0, you're going to end up with a first order differential equation with a constant forcing function. Now the solution to this differential equation is very simple. Basically it will have this form, f of t. If you solve for f of t will equal to a times e to the minus t over tau. Tau is this coefficient here, plus some DC value b. That DC value, we call it the forcing function or the forced response, which is caused by this k. This term over here is the natural response, or basically the transient response, and it is mainly caused by the initial condition. Now this is basically the solution to this differential equation, first order differential equation with constant forcing function. You will end up with this solution. So tau is basically a constant that depends on the inductor and the equivalent resistance seen by the inductor after switching. So basically we say that tau will equal to L over R equivalent, where R equivalent is the equivalent resistance across the inductor after switching. And to find the equivalent resistance, you need to suppress all the sources. So if you have voltage sources, in this case after switching, you got to short those sources. If you have current sources, you got to keep them open. Now that is a very basic technique of finding R equivalent of a circuit. You need to suppress the independent sources to find R equivalent. So R equivalent across the inductor will be the resistance across the inductor after suppressing the voltage sources in this case. And keep in mind that this is going to be basically after switching. Now we are interested in solving for A and B. So to solve for A and B, we're going to basically be a little bit clever about it. We know that this term here is the transient response caused by switching, while B is basically a DC value that is triggered by the forcing function K. Basically those voltage sources after long time will cause the response to be B. So the way we do that, we say that if t equals infinity, this terms becomes 0. So B is basically the response at infinity. Now to solve for A, we know that this is at infinity. To solve for A, we will say that what's the response at 0. If we know what's the response at 0, then we can say that A plus B will equal to the response at 0. Or basically you say that A plus F at infinity is equal to F at 0. Then from here we can solve for A. So basically the general solution says that F of t will equal to A, which is F at 0 minus F at infinity, times e to the minus t over tau, plus F at infinity, which corresponds to B here, for t greater than 0. This is the general solution for the step response of RL circuit. So when you solve for RL circuit, the trick is to solve for IL. Solve for IL first, the inductor current. And the reason is that it is easy for us to obtain the initial conditions and the response at infinity. For the inductor current, we can say that IL of t will equal to IL at 0 minus IL at infinity times e to the minus t over tau plus IL at infinity. Now keep in mind that the inductor's current is continuous, so IL at 0 is the same current through the inductor before switching. So before switching, the inductor behaves as a short circuit, and we can solve for that inductor current. And once we solve for the inductor current before switching, it is the same as the inductor current just right after switching. So IL at 0 plus is the same as IL for t less than 0. Also, at t equals infinity, the transient term have vanished. So the transient term here has vanished, and all what we have is basically a DC value. Then at t equal infinity, the inductor is also short circuit. The only difference about the circuit is that you're gonna draw the circuit after switching. So in this particular circuit, the 5 volts is applied to the circuit after switching, and the inductor gonna be short circuit. So basically, if you wanted to solve for RL circuit, there is 3 elements you need to find. The first thing is you need to find IL at 0 plus, which is the same as IL at 0 minus. You need to find IL at infinity, and you need to find tau. If you solve for that, you solve for IL of t. Once we solve for IL of t, we can solve for VL. VL is basically L times di dt. We can solve for V4. V4 will equal to IL times R4. We can do KVL here to solve for this voltage. We can solve for the current in this resistor. It will equal to the 5 minus this voltage over this resistor. You can solve for the current through R1. It's basically going to be 10 minus this voltage over that resistor. So if you solve for IL in this circuit, you solved for everything else. You just need to apply KVL, KCL, and Ohm's law to solve for any voltage or any current in the circuit. So let's solve this example numerically, and let's show you the steps to do that. So here is the circuit, that's what we have, and the first thing we're gonna do is we wanted to find the initial current for t less than 0. So if you look at the circuit here carefully, you know that the switch was basically connected to this leg for t less than 0. For t greater than 0, the switch moves to the 5 volts. So basically after switching, we have added the 5 volts to the circuit. Before switching, this 5 volts was short circuit. So for t less than 0, we're gonna draw the circuit where this switch gonna be short circuit, but also the inductor gonna be short circuit, because before switching there is no change in the circuit and the circuit is DC, then the inductor is short circuit. So this is what we have before switching. Basically the 5 volts is gone, is shorted, and the inductor is short circuit. Everything else in the circuit is the same. So the question now, we need to solve for IL. So you need to look at the circuit and you need to find the technique to solve for the current through the inductor. So my technique was to solve for the equivalent resistance of the circuit And once I solved for the equivalent resistance of the circuit, I can solve for Ix, which is the same current comes in from the 10 volts through the through R1, and then this current we're going to call it Ix. And once I solve for Ix, I will be able to solve for IL using the current divider. So now I can say that Ix basically will equal to the 10 volts over R equivalent. And if you look carefully here, you can see that R2 is in parallel with R3 is in parallel with R4. Then we can say that Ix will equal to the 10 volts, which is this voltage source, over the equivalent resistance, and the equivalent resistance of the whole thing going to be the 2.2K plus the 1K for R2 in parallel with the 1K of R3 in parallel with the 470 ohms, and this was equal to 4.1 milliamp. Now I solved for Ix, and I know those two resistors are in parallel. So 1K in parallel with 1K is 500 ohms. So those two going to be replaced with 500 ohm resistor. Then I can tell you that IL will equal to, using current divider, the opposite equivalence resistance over the sum times the total current. So using the current divider, I can say that IL at 0 will equal to the opposite resistance, which is the sum of those two in parallel, that is 500, over the equivalent resistance, which is the 500 plus 470 times Ix, which I just solved for earlier. Now this will equal to 2.11 milliamp. So initially, before switching, the current through the inductor, which is this current here, is 2.11 milliamp. This is the first step you need to do. It's the initial condition that we are solving for. Now the second step is basically to draw the circuit at t equal infinity. So if you look at the original circuit, at t equal infinity, which is for t greater than 0, we have added the 5 volts to the circuit. And at infinity, the circuit is DC again. So this inductor becomes a short circuit as well. So if we draw the circuit, this is what we have. We have the 10 volts connected to the 2.2 K ohm, and the 5 volts is added to the circuit, and then the inductor is short circuit again over here. So now we need to solve for IL, and this is a new circuit, so we need to analyze the circuit using a new technique. Looking at the circuit, I have 2 voltage sources, and I only have one unknown node, which is this node. It's better than the 3 meshes that I have. So I will use nodal analysis here. So I will define this node over here to call it Vx. This is my Vx, and now I'm going to write the equation for Vx. So nodal equation for Vx. So I will say that Vx minus 10 over 2.2, that's what I have here, plus Vx minus 5 over the 1K, this is what I have here, plus Vx minus 5 over 1K, plus Vx over 1K, which is what I have here, plus Vx over R4, which is the 470 ohms, that's what I have here, which equals to 0. This is a single node circuit, so I basically solve for Vx, and now Vx will equal to 1.083 volts. So I was able to solve for Vx. Once I solved for Vx, which is the voltage here, then I can solve for IL. IL at infinity, which is the current through the short circuit, is the same as the current through R4. Then we can say that IL at infinity will equal to Vx over 470 ohms, which will equal to 4.432 milliamps. So let's step back a little bit. We say that we solved for IL before switching, and then we said that we're going to solve for IL at infinity. So we end up solving for 2 parameters for the general solution. The third step is to find tau and R equivalent. Now to find R equivalent, we need to draw the circuit after switching, and we need to suppress those voltage sources so they become short circuit. So this is how the circuit will look like. We say that we're going to draw the circuit after switching So after switching, the switch gonna be at this side, but we're gonna suppress the 5 volts, so it becomes short circuit, and we're gonna suppress the 10 volts, which becomes also short circuit, and then we need to look for R equivalent across the inductor. So the best way to do it is you remove the inductor as I showed you here, and then look for R equivalent across the inductor. So if you look into the circuit, to find R equivalent is very easy for us to do. This resistor, and this resistor are all in parallel, which is in series with R4. So we can say that R equivalent will equal to the 2.21K in parallel with the 1K in parallel with the 1K plus the 470 ohm, and this will equal to 877 ohms. Now we solve for R equivalent. We can solve for tau. Tau will equal to L over R equivalent, and L is equal to 1 millihenry, then tau will equal to 1.14 microseconds. Basically at this point we can solve for IL, because we know that IL of t will equal to IL at 0 minus IL at infinity times e to the minus t over tau plus IL at infinity. I know what IL at 0 is, I know what IL at infinity is, and I know what tau is. So when I plug in those values, IL of t will equal to minus 2.23 times e to the minus t over tau plus 4.432 milliamp for t greater than 0. This current is after switching. Before switching, the inductor current is DC, but after switching for t greater than 0, it will have this form. So now we know what's the solution to the circuit is. Let's validate that using PSPICE Orcad. So I have loaded PSPICE Orcad now, so I'm going to start a new project. So I will go to new project, and in this project I will say that we can give it a name. We can say that RL step 1, just give it any name. We make sure that's a PSPICE analog. Click OK. We're going to create a blank project. Click OK. Now we're going to draw the circuit. So I'm going to start with the DC voltage source, the first DC voltage source. So I'm going to call it VDC. And this basically going to be at 10 volts. And then I'm gonna basically use the switching circuit, and the switching circuit basically gonna be V pulse. So I'm gonna have the V pulse over here, and let me zoom in a little bit to show you what are the values for the switching circuit we're gonna have. So the switch basically was 0 before switching, so we're gonna say that V1 equals 0. And then it became 5 volts. Then we're going to say that V2 will equal to 5 volts. I'm going to start the simulation after 10 microseconds. We're going to say that this pulse is very fast, so it will take 1 nanosecond for time rise, 1 nanosecond for time fall. Then what I'm going to do here is I'm going to make the pulse width to be very large. Like let's say that it is 1 second. So the pulse will take for a long time, much longer than the time constant that we have. And then what I'm going to do is we're going to say that the period going to be 2 seconds. So the idea is that when we run the time simulation, we will never run it to 1 second. We will run it around 10 times tau. In this case, we can say that we can run it up to like 20 microseconds. That's more than 10 times tau. That's like 15 times tau, because tau was 1.14 microsecond. So it will never reach the end of the pulse width. So we will never see the square wave. This is another trick here when you want to simulate a complete switch. Now remember that when you build this in the lab, you're gonna have basically a rectangular pulse. So you're gonna see a rectangular pulse, so you wouldn't use this slow pulse. It's not basically very effective. You're probably gonna use like a pulse width of 20 microsecond or a period of 40 microsecond when you build a circuit in the lab. However, for simulation we can do that here, and that's really good. So then we're gonna basically connect the resistors. So over here we're gonna have 4 resistors. The first resistor is R1, and R1 was 2.2K. Then we're gonna have R2 over here, which is 1K, and then we're gonna have a resistor over here which is R3, and then we're gonna have a resistor over here which is R4. So let's enter the values. The first one gonna be 2.2K, and then this is 1K, this is 1K, and this gonna be 470 ohms. And then we're gonna have inductor, so I'm gonna add L, and L is basically gonna be 1 millihenry, so I will do here 1 M. And now we're gonna connect the rest of the circuit. So this 10 volts will go to R1, and this rectangular pulse will go to R2. Those two will come over here, and then this is the inductor. That is the inductor. So let's connect the bottom node, which is the ground node. So this is our ground node, connecting basically the 10 volts to the V pulse, to R3 to R4. Let's make sure that this is connected here. And then we're gonna add a ground. We have to have a ground when we use PSPICE. So this is the circuit that we're gonna simulate. I'm gonna save it, and then I'm gonna create a new simulation. So click on new simulation. I will call it sim1, and then I'm gonna basically run the simulation up to 20 micro. So 20 micro is really a good number, because we know that the time constant for the circuit is 1.14 microseconds. Then actually we are running the simulation for roughly 15 times tau. Usually we assume that we reach infinity for t greater than 5 tau. So around the 7 microseconds we assume that's infinite. 20 microseconds is actually way more than that. I will say that the maximum step size is going to be 1 nano. So basically this is a very small resolution, so you can have smooth curve. So we're going to say apply, okay. Now I'm going to add a current probe. I'm going to basically connect that to the inductor. We're going to measure the inductor current, and let's run the simulation. Hopefully we'll run with no errors. So let's see what we have. And this is what we have. So you can see that the current initially starts at roughly 2.1 milliamp, and then it will reach some final value to around 4.41 milliamp. So it jumps from this initial value to that final value. That's why we call this particular circuit the step response. Let me thicken the line a little bit. I'm going to select the line, I'm going to right click on it, and then I'm going to come into the trace properties, and then over here I can change the width. I want to make it a little bit thicker so you can see it. So it's a thicker line. So let's show you how we do that. We click on the line, we select it, then we do right click on the mouse, we go to trace property, and you can adjust even the pattern. If you want it dotted, you can. So let's make it dotted. You can change the color if you want it, but let me go ahead and change it to a straight line. I like the straight line more. Trace property, I'm going to make it straight line. You can also add the symbol for the data. You can change the color. If we want to make it, for example, red, let's see if we can do that. So it's red color. The trick here is that it's a step response. So the current will jump from some initial value for t before switching. The switching happened at 10 microseconds, and it will jump from this initial value to this final value, and it will do that exponentially. This is the exponential curve. So it will jump from some initial value to some final value. And this is what is so important about the circuit. Now, the time required to move 63.2% from this peak to peak value, from the initial value to the final value, the time required to move 63% is called tau. So tau is the time required to jump 63% from the initial value to the final value. Basically, we have shown you an example of how to solve RL circuit. So this circuit wasn't very trivial, but it was easy to solve following the steps I have shown you. Now, once we solved for the circuit analytically, we were able to simulate the circuit in Orcad, PSPICE, and our simulation results matched our calculations. I hope you liked this video, and good luck to you. Thank you.